This is the look how smart you are portion of the event. So, at this point in the year in chemistry, you can easily look at the periodic table for any element and tell me how many electrons it's starting off with. You can easily look at it, tell me what group it's in, and figure out how many valence electrons it's got. You can draw me multiple representations of its valence electrons and how many it's got. You can predict how many valence electrons it's going to give up or gain or all those things. So not only have you done all that, you've also got a number of ways to represent these things. And what we're going to do today is, and I forgot to print the learning goal, so it's out there, but I'll let you know, and I'll have it printed on Monday, that by the time we get through this chunk, you're going to be able to look at any molecular compound I give you, and you're going to be able to represent it structurally using something called a Lewis dot diagram. And I'll tell you a little bit more as we go about what else that will allow you to do. But I wanted to run back and hit all the things you do know how to do, because we're going to just find one more, for now, way of representing atoms. So we've got a lot of different ways to represent atoms, and we're going to add one more to the tool belt. So this is something called an electron dot diagram, and you have probably actually already done this. And an electron dot diagram, or an electron dot notation, just shows valence electrons. That's all it shows. So, Mr. Tomlinson, pick your favorite main group element. That's group 14 or below. Okay, I'll tell you what. I love sodium. Sodium's awesome. Tastes delicious in many compounds. Does exciting things when added to water. You can't go wrong with sodium, right? So, you know what the symbol for sodium is. Na. And based on its location in the periodic table, group 1. Don't yell it out. Show me with fingers, how many valence electrons does sodium have? 1. Well, here's the way this works. I'm just going to jot down 1 valence E. When we do electron dot diagrams, the first thing you start off with is the symbol for the element, which we've already got. And then for every valence electron that element has, we draw a dot. Hence why they're called electron dot diagrams. So for sodium, this is really pretty easy. Ta-da! You're done. Now, I want to talk about a couple ideas, like how we customarily represent something and reality. So this represents sodium with 1 valence electron. Now, if we were able to look at sodium atoms in some sort of high-powered device, would they say Na? No. This is a representation of reality. It is not reality itself. I'm going to continue to say this. So what we've done here is we've represented sodium with 1 valence electron. When we represent things through electron dot diagrams, there are some things that we customarily do. Like when we're drawing our electron dots, we customarily, traditionally start at the top and go clockwise. Now, of course, in the case of sodium, there's only 1, but if we have more than 1, and we will shortly. Now, let me ask you this. For other things in group 1, like potassium, what's their electron dot diagram going to look like? It's going to look really similar. Everything in group 1 is going to be the symbol with 1 dot. Okay. Easy breezy. So, pick your favorite group 2. Here, and I'll bring that over. And we know that that would look the same the whole way down the group. Pick your favorite group 2, Rachel. Group 2 element. Calcium. Okay. So calcium has 2 valence electrons because it's in group 2. And again, calcium atoms don't say Ca in the middle. But when we're starting off with something that has 2 electrons, we traditionally start at the top, and we traditionally go clockwise. So an electron dot diagram for magnesium would look the same. Now, again with this idea of representation versus reality. Does that mean that a magnesium atom has 1 electron on top and 1 electron on the right side? No. I keep stressing that because this is like building a glorious castle made out of Legos with a 2-year-old, something I have personal experience with. The minute you get this beautiful thing built, it's going to get smashed into pieces. So we customarily start at the top, we customarily go clockwise. What we're going to do next is to move those dots all over the place. And every year somebody kind of freaks out and goes, but it goes there! No, it doesn't. They're representations, they're not real electrons. So the important thing to remember is that they represent reality, they aren't reality. Okay, so the rest of group 2 will all look the same. Now, we're skipping over the D block, because remember the D block and valence electrons, it doesn't line up the same way. It's a little different. So if we go to group 13, Kiara, name me your favorite group 13 element. Boron, okay. Boron. Group 3, how many valence electrons? Or group 13, sorry? 3. 3 valence electrons. And again, we customarily start at the top and we customarily work our way around clockwise. And this is not letting me do this easily. There's boron. And everything else in group 13 is going to look the same. Somebody in the other class said, can we have a 200-point test on this? I can do this. Yeah. Okay. Group 14. We got some of my favorites in here. Ella, pick me your favorite group 14 element. Carbon. Good choice, ma'am. Good choice. Being a carbon-based life form such as yourself. Okay, how many valence electrons? 4. So, starting at the top, going clockwise, looks like that. And everything else in that group, same thing. Well, this is easy so far, right? When we go to group 15, so, Mr. Bell, name me your favorite group 15 element.
Phosphorus.
Phosphorus. Excellent. Glowy phosphorus. How many valence electrons? Show me with fingers. 5. Okay. So 5 valence E. And again, we start at the top, traditionally. I should make this that. There, that's easier. And then we go clockwise around the sides. Well, now we have 1 on each side. This is when we start to double up. So once we get to the point where we have 1 on each side, we do double up. So everything in group 15, and nitrogen is the one that's you see a lot of. You'll see phosphorus sometimes, but we use nitrogen a lot. And let's see, I want no opacity. Bigger. Okay. And, you know, as you get better at doing these, you'll shortcut it and just do that. We'll come back to group 15. Okay, group 16. Some critical stuff in there. Ms. Meredith, name me your favorite group 15 or group 16 element. Oxygen. Again, nice choice, being an oxygen-breathing organism such as yourself and all. So, you get the hang of this, right? We start at the top, we go clockwise, we put 1 on every side until we've got 1 on every side, and then we start doubling them up. Okay. That's easy. Now, you will see oxygen written like that. Does it matter? Because they're not reality, they're representations of reality. What this is trying to show is that these two electrons want to be as far away from those two electrons as possible, and so people will write it that way, but it's also three-dimensional, and what we're drawing here is two-dimensional. So it doesn't matter. It does not matter. Again, not reality, just a representation thereof. Okay, that was group 16 with 6 valence electrons. So now we get to the big fun. The halogens. Everybody loves the halogens. Ms. Bell, name me your favorite halogen. Chlorine. Okay. Excellent choice. Very common, readily available. We use it a lot. We all know what it smells like. So how many valence electrons? 7. 7 valence electrons. 7 valence electrons. I'll have to move this down a little bit. So, same thing. We do one on each side. Boop, boop, boop. Until we don't have any choice but to double them up. Does it matter where that apparent blank space ends up? No. Could that blank space be on the top or the side or the bottom? Yeah, that's fine. Again, not reality, just a representation. I know it seems ridiculous that I'm stressing that. You'll understand why soon. Okay, so that's our chlorine. We've got one group left to talk about. Everybody wants to be like them. They're the cool kids. Hey, Kaylee, name me your favorite noble gas. Neon? Neon? Okay, yes. It's purty. It glows. It's awesome. How many valence electrons does it have? 8. 8 valence electrons. Well, this is easy. This is intuitive. You guys all know how to do this. There's really nothing to it. Okay, so we've got 8 valence electrons there. There are no choices. There are 2 on every side. You know, we imagine this as sort of a squared off box, and we show 4 sides representationally. Reality is obviously more complicated than that, but this is our representation of it. Just like all the different ways that you've learned so far to represent electron configurations, to represent the atom itself, everything from the Bohr model with all the little rings, up through the crazy quantum model with the tennis ball and the cotton candy, each one of these ways of representing reality allows us to do something different with it. Okay, awesome. We can draw dots, Moser. So, what this allows you to do is the next step we're going to take. So I said your learning goal, the learning goal we're working on in this chunk is that by the end of this chunk you will be able to draw any molecular compound represented with something called a Lewis dot diagram, or a Lewis structure. What electron dot diagrams do is allow you to draw Lewis structures. Lewis structures are just a kind of visual formula for an atom. Again, it's one more, or for a compound, it's one more way to represent compounds. The nice thing about Lewis structures, the things that it allows, if you are going on in chemistry, if you are someone who is going to take organic, or you're somebody who's going to major in chemistry or chemical engineering, having this visual image of the structure of a compound allows you to make predictions about its behavior. And if you get up into like physical chemistry, where you're actually doing the physics of interactions between compounds, which is just like as horrible as anything could ever be, you will use this knowledge of their structures to help you. If you're not going any further in chemistry, which many of you aren't, this will help you in chemistry, especially if visual is one component of your learning style, because having this visual representation of a compound, or especially a polyatomic ion, makes it concrete. So when I didn't used to stress this as much as I do now, And I remember having some folks at near the end of one year who still didn't quite have a grasp on a particular concept, and I realized that stressing this a little bit more would have helped them. And so now I stress it more. Because it really will. It will give you something to sort of grip onto as you're climbing the mountain of chemistry. It gives you a nice little foothold to go, oh yeah, okay, I understand what that is because I can draw it. So at its simplest, well, I'll tell you what. We'll draw a very simple Lewis structure. You remember carbon, our old friend? Hello, carbon, my old friend. I've come to breathe you out again. Get it? CO2? Never mind. So we've got carbon, 4 valence electrons. There's our little carbon. And if you think back and remember, what does carbon want to have around it to feel comfortable, satisfied, and happy? How many? The what rule? It wants 8, the Octet Rule. Basically, it wants to look like that. Everything wants to look like that. And that gives us a nice visual image of what all these atoms want in essence. And remember, we're using a metaphor here. Atoms don't want anything. They don't want a cookie. They don't want more electrons. They just are. But this is the point at which it would be most stable. So we go back here. We've got carbon. Now, carbon is cool stuff. I mean, and I'm not just saying that because I'm a carbon-based life form and I'm biased, though of course you can't help but be. Carbon has 4 places where it can bond to something else. And carbon bonds, we said, with itself and with hydrogen a lot. So let's look at hydrogen. Remember our old friend hydrogen? How would you draw a Lewis dot for hydrogen? That was hard. There's hydrogen. Well, we've got hydrogen, and what does hydrogen want to share to get to? It wants to be like helium. So hydrogen just wants to get 2. If hydrogen could get 2, it'd be really happy. Well, hydrogen comes along. Oopsie. And it shares one of those with carbon. So now at this point, that hydrogen feels like it has both of those electrons. And that carbon feels like it has both of those electrons. Huh. Well, what we very often see then is this little molecule. Okay, and that's methane. Oops. That's methane. It's 1 carbon bound to 4 hydrogen. And it's natural gas, it's also cow farts, it's a whole bunch of other things. It's the simplest organic molecule we can make, 1 carbon, 4 hydrogens. So if we look at that carbon, remember that that carbon wanted to be like neon, right? Well, if we look at carbon, carbon feels like it's got 2, 4, 6, 8 electrons. Is carbon satisfied? Yes. And hydrogen wants to feel like it's got 2 electrons. So this hydrogen feels like it's got 2, it's happy. This one feels like it's got 2, it's happy, happy, happy. Everybody's happy. That's the structure of methane. Now, each of these little pairs, when we're finished with a Lewis structure, wherever we've got a pair that's shared between 2 atoms, we change the representation. We no longer draw both dots. We just draw a little line. So methane is drawn like this. And each of those lines represents a pair of electrons. It represents a pair that's shared. It's a single bond. Okay. Not so bad. So that's our finished Lewis structure for methane. Let's try something a little bit more interesting. Let's try ammonia. How many of you have had exposure to household ammonia? I don't know if it's as common as it used to be as a cleaning product. It smells awful, but it cleans things really well. It really cuts grease. And ammonia is one nitrogen atom bound to 3 hydrogens. And as a first step in writing a Lewis structure, it's often, not always, but it's often helpful to write the electron dot notation for each of these. So for nitrogen, you'll remember we had, whoops, that. And for hydrogen, of course, we had that. Can you see any place where it looks like a hydrogen might fit in to share here? Yeah, this one's really, it's really intuitive. So we take our little hydrogen, la 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 la, oopsie. And there's one. And then we put another hydrogen here. Another hydrogen here. And lo and behold, we have ammonia. Now, any of those pairs that are shared, we can change to a line. How many lines are we going to put in here? 3. Okay. We have to put that pair back on nitrogen. Is nitrogen sharing that pair with anyone? No. And it's called an unshared pair. Okay? It is called an unshared pair. And we can't represent unshared pairs with lines. We only represent shared pairs with lines. So that's about as far as the other class got because of complicating factors. I have added some homework problems, and I'll add a few more that have to do with these. I'll give you the rest of the time to work so that we stay at the same spot, and that's it.